The beginning of everything should have been the messiest moment in history. It wasn't. It was the most orderly moment this universe has ever known, and every single second since then, it has been coming apart, slowly, quietly, irreversibly. Sit with that for a moment, because it's backwards. Beginnings don't arrive pre-organized. Explosions don't produce arrangement. Nothing in your experience starts neat and decays into structure. It starts rough and falls into ruin. And yet the first instant of everything we can see was cleaner, smoother, more precisely balanced than anything that has existed since. So physicists did what physicists do. They went looking for the reason. They built theories that could explain where that order came from. And some of those theories are stunning, elegant, testable, still standing today. But somewhere in the middle of all that work, a suspicion began to surface. The theories weren't removing the mystery. They were moving it. Every explanation for the order at the beginning quietly required its own order, one layer further back, hidden inside the assumptions. The problem never got solved. It got relocated. You're watching Dream Trips. And what makes this uncomfortable isn't the paradox itself. It's what comes with it. Because there are three things about this universe that, by every reasonable expectation, should not be true. The smoothness. The asymmetry. The observers. We'll get to all three. But before any of that makes sense, we have to talk about the picture in your head right now. Because it's wrong, and it's wrong in a very specific way. Close your eyes for a second, and let the picture assemble itself. Because you already have it. Everyone does. There's darkness first, not night. Night has stars in it. This is the other kind. An empty room the size of forever, with nothing in it and no walls to hold it. Black in every direction, and silent in a way that has no word attached to it yet. Because silence needs air, and there isn't any. And somewhere in the middle of all that, nothing. There's a point. Small. Impossibly small. Smaller than a grain of sand. Smaller than an atom. A single bright pinprick, suspended in the dark, like the last ember of a fire that hasn't been lit yet. Everything that will ever exist is folded up inside it. Every star, every galaxy, every ocean, every mountain range on every world, every creature that will ever open its eyes and wonder about any of this. All of it, compressed into something you could lose between your fingers. And then, the countdown. You've seen this in 100 documentaries, 100 films. The music drops out. The camera drifts closer. And then, detonation. A wall of white fire tearing outward in every direction. Debris flung across the void, at speeds that make light look patient. Matter screaming outward through the empty dark, cooling as it goes, clumping, catching, spinning up into whirlpools of gas that will one day be galaxies. The shockwave keeps expanding. The room stays still. The universe rushes out to fill it. It's a magnificent image. It's cinematic. It's dramatic. It's the single most famous scene in the history of science. And almost every part of it is wrong. I want to be careful here, because this isn't a story about scientists being fools. The people who worked this out were not confused. The image in your head was never the theory. It was the marketing. It was what happened when an idea too strange to picture got handed to people who needed a picture. And the name didn't help. Big Bang. Two words that promise a sound, and a blast, and a moment of violence, none of which happened. The phrase wasn't even meant kindly. It was tossed out by an astronomer who thought the whole idea was ridiculous. And it stuck the way insults sometimes do. And now it's carved into every textbook on Earth. A joke that outlived the joker. So let's take the picture apart. 3 pieces, each one worse than the last. The first thing to go is the room. In your mental image, there is space, dark, empty, waiting, and the explosion happens inside it. That's what an explosion is. A thing happens somewhere, and the somewhere was already there. A grenade in an empty warehouse. The warehouse doesn't participate. It just watches. But there was no warehouse. Space was not the stage the Big Bang happened on. Space was the thing that was happening. It wasn't a container that got filled. It was the expansion itself, unfolding, stretching, creating distance where distance had not existed a moment before. Nothing flew outward into anything. Because there was no outward, and there was no anything. I know how that sounds. Your mind keeps trying to zoom the camera back, to see it from outside. There is no outside. There is no vantage point. No observer floating in the dark watching the universe inflate like a balloon. Every camera position you can imagine is already inside the thing that's growing. And this isn't philosophy. It's measurable. When astronomers look at distant galaxies, the light arriving from them is stretched, shifted toward the red end of the spectrum. And the farther away the galaxy is, the more stretched that light becomes. Not because the galaxies are racing away through space like shrapnel, because the space the light has been crossing for billions of years has been quietly getting longer underneath it. The entire trip, the light didn't change. The distance did. That's the first blow. There was no room. The second one is stranger, and it's the one that tends to make people go quiet. If there was an explosion, there was a place where it happened. A center. Ground zero. You could, in principle, point at it. A specific coordinate in the sky. A direction you could turn your telescope toward and say, there. That's where it started. Every astronomer in history has looked. There is no such direction. And not because we haven't found it yet, because the geometry doesn't allow one. If space itself expanded, then every point that exists now was in that dense, hot beginning. Not near it, not adjacent to it, in it, all of it, everywhere, at once. Which means the Big Bang did not happen far away, and long ago. It happened here. It happened in the room you're sitting in. It happened in the space occupied by your chair, and the air in front of your face, and the few centimeters between your eyes and this screen. Every one of those locations was, at one time, part of a state so dense and so hot that atoms could not hold themselves together. That patch of space didn't travel here from somewhere else. It was always this patch of space. It was just smaller. All of it was. Look up tonight. And you're not looking outward from the site of the explosion. You're looking backward through a thing you're standing inside of. You are not a spectator to the Big Bang. You are made of it, and you're sitting in it. And it never stopped. 2 blows down. No room. No center. Now the third one. This is the one. Everything else in this film is built on top of. So I want you to feel the weight of it. It was not violent. The word bang implies chaos, turbulence, shrapnel, and roar, and the ugly randomness of things being torn apart. That's what explosions do. They take a structure and convert it into mess. It's practically the definition. The early universe was the opposite of a mess. It was hot, extraordinarily, unimaginably hot. But hot is not the same as chaotic. Hot means fast. Chaotic means uneven. And the early universe was almost perfectly, eerily, even. Smooth in a way that nothing in your experience has ever been smooth. We can actually see this, which is the part people find hard to believe. There's a faint glow filling the entire sky in every direction. The oldest light there is, released when the universe first cooled enough to become transparent. And it has been traveling ever since. It's been mapped in extraordinary detail. And when you look at that map, at the temperature of that ancient light from one side of the sky to the other, the variation is about 1 part in 100,000. Let me put that in something you can hold. If you shrank the ocean down to the size of a marble, and it kept that same relative smoothness, the waves on it would be smaller than a bacterium. If you built a billiard ball to that tolerance, it would be the most perfect object ever manufactured on this planet, by an enormous margin. Nothing you have ever touched is that smooth. Nothing in the sky today is that smooth. Not a star, not a planet, not a droplet of water. The beginning of everything was smoother than anything that has existed since. And here's where it stops being a fun fact and starts being a problem. Because if you'd handed the laws of physics to a mathematician and asked them what a random beginning would look like, no assumptions, no preferences, just all the possible ways a universe could start, drawn out of a hat. Smooth is not what comes out. Lumpy comes out. Violently, catastrophically, lumpy, overwhelmingly. Almost every possible starting condition is a disaster. Matter clotted into black holes before anything could form. Gravity collapsing whole regions, instantly. No galaxies. No stars. No chemistry. No time to speak of. The smooth beginnings aren't just rare in that hat. They're so rare that the number describing how rare has no useful comparison in ordinary language. You would not draw one by accident. Not in a trillion universes. Not in a trillion. We drew one. So now, turn around and look at where that leaves the story you were taught. The version most of us absorbed goes like this. The universe began in chaos, and slowly, patiently, order emerged from it. Structure fought its way up out of the mess. Complexity climbed the ladder. Life is the triumphant end of a long war against disorder. It's a beautiful story. It's also almost exactly backwards. The universe began in order, extraordinary order, and in every moment since, it has been losing it. That's what the arrow of time actually is. When you strip the poetry off it, why you can remember yesterday and not tomorrow. Why a cup shatters on the floor and the pieces never gather themselves back up onto the table. Why heat flows from hot to cold and never the other way. None of that comes from the equations of physics. Most of them run just as happily backwards. It comes from one single fact. Things started out extremely orderly, and they have been running down ever since. Time has a direction, because the universe is falling away from where it began, which means every beautiful, structured thing you have ever seen is not a victory over chaos. It's a withdrawal. Galaxies didn't build themselves against the current. They formed because tiny imperfections in that near-perfect smoothness, those 1 part in 100,000 ripples, gave gravity something to grip. And gravity pulled, and the smoothness began to curdle into clumps. Clumps became clouds. Clouds collapsed into stars. Stars forged the carbon and the oxygen and the iron, and scattered them when they died, and some of that debris ended up as a rocky world with liquid water on it. And eventually, as the cells in your hands, every one of those steps consumed order and gave back disorder. The sun is not creating energy for you. It's spending a reserve, converting a beautifully concentrated store of it into scattered, useless warmth, radiating out into a cold sky. Every meal you eat, every thought you have, every heartbeat, all of it is paid for out of the same account. We are not builders. We are spenders. Everything alive is an elaborate, gorgeous, temporary way of taking order and turning it into waste heat. And the entire structure of the cosmos is running on a balance that was deposited before the first atom formed, which leaves exactly one question standing. Who made the deposit? Because that inheritance is real. It's measured. It's in the sky, right now, mapped to a precision that would have been unthinkable a century ago. Nobody is arguing about whether the early universe was smooth. The argument is about something much more uncomfortable than that. The argument is that we have no accepted explanation for why. No established reason the universe should have opened in a state so absurdly, improbably ordered, that everything we care about became possible. It's not a gap someone forgot to fill in. Serious people have spent entire careers on it, produced brilliant work, and the honest ones will tell you the same thing. The question is still open. Where did the order come from? What bank was it drawn from? And why does every attempt to answer that seem to require assuming exactly the kind of order it was supposed to explain? Now, everything I'm about to spend the next hour questioning, I need you to understand that it's real first, because a documentary that attacks the Big Bang without proving it is just noise. So let me prove it. I want to be honest with you about what I'm doing here, because the next hour of this is going to look from certain angles, like an attack. I'm going to spend it pulling at the Big Bang, poking at the places where the story doesn't close, naming the things it can't account for, and refusing to let them go. And there's a version of that which is worthless, the version where someone announces that scientists are wrong, waves at a mystery, and walks away feeling clever. That's not an argument. That's a mood. Doubt is only worth something when it's expensive, when you've earned the thing first, understood exactly how well it works, and then found the place where it strains. So before I question any of it, I'm going to prove it, properly, not with a summary, with the actual evidence, in ascending order of how hard it is to argue with. And by the end of this, I want you to be more convinced of the Big Bang than you were when you started. That's the point. The doubt that comes later only matters if the foundation underneath it is solid. Start with the oldest thing anyone has ever seen. For the first few 100,000 years, the universe was opaque. Not dark, the opposite. It was flooded with light, drowning in it. But the light couldn't go anywhere. Everything was hot enough that electrons couldn't stay attached to nuclei, and free electrons are ferociously good at scattering photons. Light would travel a tiny distance, hit something, bounce, hit something else, bounce again. The whole universe was a glowing fog, bright in every direction, and you couldn't have seen your hand in front of your face. Then it cooled, not suddenly, over a long, gradual slide. The temperature dropped until the electrons finally slowed enough for nuclei to catch and hold them. Atoms formed, and in that moment, the fog cleared. All that trapped light was released at once. In every direction, from everywhere, at the same time. And it's still going. It never stopped. It's been crossing an expanding universe for something like 13.5 billion years. Stretching as it goes. The same stretching we talked about. The wavelengths pulled longer and longer by the growth of the space they're crossing, until what began as a fierce orange glare has been drawn out into faint microwaves, cold ones, just a few degrees above absolute zero. It is arriving right now. It is passing through the room you're in, and through your body as you listen to this. Point a sensitive enough antenna at any patch of sky at all. No stars in it, no galaxies, nothing, and you'll pick it up. A whisper from the moment the universe became transparent. That's the cosmic microwave background. And the fact that it exists at all is a serious problem for anyone who wants to claim the universe didn't have a hot, dense beginning. It's not an inference. It's not a model. It's a signal. But its existence isn't the part that matters most for this film. The part that matters is how uniform it is. Map that glow across the whole sky. And this has been done, repeatedly, with increasingly obsessive precision by successive generations of satellites. And you find the temperature is essentially the same everywhere. The variations are around 1 part in 100,000. Take a patch of sky over here, and a patch of sky in the exact opposite direction, and they agree to something like 5 decimal places. Now sit with what that means, because it's easy to hear the sky is uniform and think, well, of course it is. It isn't, of course. It's very close to impossible. Those 2 patches of sky have never met. That light has been traveling toward us for the entire history of the universe. Which means the region that emitted the light on the left and the region that emitted the light on the right are separated by more than twice that distance. No signal has ever crossed between them. No heat, no light, no influence of any kind, nothing traveling at or below the speed of light, which is everything, has ever gone from one to the other. They're strangers. They have never been in contact. Not once, not for an instant, and they're the same temperature, to 5 decimal places. Think about how things normally reach the same temperature. You put a hot object next to a cold one, and you wait. Energy flows. They meet in the middle. Equilibrium is a process, and the process requires contact. 2 rooms in different countries, don't spontaneously arrive at identical temperatures. And if you found two that match to 100,000th of a degree, you would not shrug. You would start looking for the connection between them, because there has to be one. Across the sky. There isn't one. There can't be. And yet the match is nearly perfect. Hold on to that. It's going to come back. Second piece of evidence, and this one is quieter, but in some ways more damning. When you measure that ancient light, you don't just measure how hot it is. You measure its spectrum, how much energy is arriving at each wavelength. And there's a very specific curve that objects produce when they've reached thermal equilibrium, a shape that shows up whenever radiation and matter have had enough time and enough interaction to fully mix. It's called a blackbody spectrum, and physics has known its exact mathematical form for over a century. The cosmic microwave background fits that curve. Not roughly. It is the most precisely measured blackbody spectrum in existence. Better than anything ever produced in a laboratory. When the data first came back, and the measured points were plotted against the theoretical curve, the error bars were smaller than the thickness of the line drawn on the graph. There was nothing to look at. The scatter had nowhere to hide. That's not a coincidence you can talk your way around. Nothing produces a perfect blackbody spectrum, except something that has genuinely, thoroughly, reached equilibrium. So the early universe wasn't approximately mixed. It was as thermally mixed as anything can possibly be. And I want you to notice something about that phrase before we move on. Because it's going to detonate in a few minutes. Fully mixed. Completely equilibrated. Nothing separated. Nothing concentrated. No gradients left to exploit. In the language of thermodynamics, that describes a system at maximum disorder, maximum entropy, the most thoroughly randomized state available. Just leave that sitting there for now. Third piece. This one is my favorite because of the order in which it happened. Run the early universe backward, and you reach a window, the first few minutes, where it was hot enough for nuclear fusion, but had cooled enough that the products could survive. Nuclei forming, colliding, building, and then, quickly, the expansion cooled everything past the point where fusion could continue, and the window slammed shut. You can calculate what should come out of that window. The physics is well understood. The nuclear reaction rates were measured in laboratories on Earth. Feed in the conditions, run the numbers, and you get a prediction, roughly 3/4 hydrogen by mass, roughly 1/4 helium, and traces, small, specific, calculable traces, of deuterium and lithium. That prediction was made before the measurements existed. Then astronomers went and looked at the oldest, most pristine gas they could find, material that had never been processed inside a star, and measured what was actually in it. 3/4 hydrogen, 1/4 helium, and the trace elements sitting right about where the calculations said they would. That's what separates a theory from a story. A story explains what you already know. A theory tells you what you'll find before you look, and then you look, and it's there. The early universe left fingerprints in the chemical composition of the cosmos, and the fingerprints match a prediction made from first principles by people who had no idea what the answer would be. Fourth, and simplest, and easy to underrate. Light has a speed. That means distance is a time machine. When you look at something a billion light-years away, you are not seeing it as it is. You're seeing it as it was a billion years ago, because that's how long the light took to reach you. Look farther, and you look further back. So we don't have to imagine the young universe. We can point a telescope at it. And when we do, it's different. Galaxies at great distances are not miniature versions of the ones nearby. They're smaller, more chaotic, more violent, still assembling. Fewer heavy elements, because fewer generations of stars had lived and died to make them. The farther out you look, the younger and rawer everything gets. Exactly as it should, if the universe has a history, rather than simply existing in a steady state. We're not reconstructing the past, we are watching it, live, at a delay. So, an afterglow that fills the sky, a perfect equilibrium spectrum, element ratios predicted before they were found, and direct visual access to earlier epochs. That's the case. It is, honestly, one of the best supported claims in the history of science, and anyone who tells you the Big Bang is a guess has not looked at the evidence. Good. Now I need one more thing established before we can go anywhere, and it's not about cosmology at all. The second law of thermodynamics. Entropy increases. Disorder wins. Systems left alone don't get more organized, they get less. Heat spreads out, structures decay, differences even out, and the whole thing grinds toward sameness. You know this law better than you know any other law of physics, because you live inside it. The coffee goes cold and never spontaneously reheats. The room gets dusty and never spontaneously tidies. The ice melts into the drink, and the drink never separates itself back into ice and warm liquid. Not once, not ever. You've never seen a single exception, and neither has anyone else. And that's not sloppy language. It's the literal state of things. The second law has never been observed to fail. Not in a laboratory, not in a star, not anywhere. There's a famous line among physicists that if your beautiful new theory contradicts the second law, then there is nothing to be done for it, and your theory will collapse in the deepest humiliation. It's the closest thing physics has to an absolute. Now, I'd like you to put two things I've just told you side by side, and I think you'll see the problem before I say it. The cosmic microwave background is a perfect blackbody, which means the early universe was in complete thermal equilibrium, which means, in terms of ordinary matter and radiation, it was at maximum entropy. Maximally disordered, as mixed as a thing can get. And the second law says entropy has been increasing ever since. Increasing from maximum. To what? Those two statements cannot both be true. If the universe started at the top of the scale, there was nowhere left to climb. The second law would have nothing to do. Time would have no direction. Nothing would ever have formed, because there'd have been no order left to spend. And yet here you are, made of structures, listening to a story about it. Something in the picture is wrong. Here's what's wrong. And this is the payoff of this entire section, so stay with me for the next 90 seconds. We left something out. We calculated the entropy of matter and radiation, the gas, the light, the heat, and we ignored the one force that dominates everything on large scales. Gravity. And gravity does not play by the rules you've internalized. It inverts them completely. Think about gas in a room, concentrated all in one corner, and that's an ordered, low-entropy state, special, arranged, unlikely. Let it go and it spreads out, fills the room evenly, and that even spread is the disordered, high-entropy state. Spread out equals messy. That's the intuition every one of us carries. For gravity, it's exactly backwards. Picture a stretched bedsheet with marbles scattered across it. Space them out perfectly evenly, and then let go. Do they stay spread? No. Every marble dents the sheet, and every dent pulls in its neighbors, and they roll toward each other and pool. Clumping is what happens on its own. Smoothness is the state you had to work to arrange, and it's the state that falls apart the moment you stop holding it. That's gravity. Left alone, matter gathers. Clumps grow. Clumps pull harder, so they grow faster. Gas collapses into stars, stars into clusters, matter into ever deeper wells, and at the bottom of that process sit black holes, which are, by an almost absurd margin, the highest entropy objects known. A single supermassive black hole contains more entropy than everything else in its entire galaxy put together. So for gravity, clumped is disordered, smooth is ordered, spread out and even is the rare, special, low-entropy state, the arrangement you would never stumble into by accident. And now go back and look at that map of the early universe again. Perfectly smooth. 1 part in 100,000. The early universe was, in matter and radiation, at essentially maximum entropy, and simultaneously, gravitationally, at almost exactly zero. That's the resolution. Both facts are true, because they're facts about different things. The thermal books were balanced, and the gravitational books were empty, and all the order this universe has ever spent, every galaxy, every star, every atom in your body, came out of that second account. That's the inheritance. That's the arrow of time. Matter had nothing left to give. Gravity had everything. Which finally lets me sharpen the question properly. It isn't, why was the universe orderly? It's much narrower and much worse than that. Why was the gravitational entropy so close to zero? Why did the universe open in the one configuration gravity finds most difficult to hold? The configuration it abandons the instant it's allowed to, when every other possibility was sitting right there. We can measure the number. We know what it implies. Nobody can tell you where it came from. And that number, the gravitational one, is where everything starts to fall apart. And it doesn't fall apart in one place. It falls apart in 3. From here on, this film has a shape, and I want you to know what it is before we start, because it's going to make everything easier to follow. There are 3 things about the beginning of the universe that should not be true. 3 anomalies. And for the rest of this, every explanation anyone offers, and there are some brilliant ones coming, from some of the finest minds who've ever worked on this, is going to be held up against all 3. Not one, all 3. That rule matters more than it sounds, because the pattern you're going to see, over and over, is a theory that handles one of them beautifully, elegantly, in a way that makes you sit up, and then you turn it toward the second one, and something goes quiet, and you turn it toward the third, and it starts saying things that are genuinely, seriously strange. So, 3 anomalies. Here they are. The first one is the smoothness. We've already established what the early universe looked like. Uniform to 1 part in 100,000. Thermally equilibrated, gravitationally almost featureless. And I've told you that this is improbable. Now I want to show you exactly how improbable, because the word doesn't do it. Imagine you could take all the mass and energy that exists, everything, the entire contents of the cosmos, and distribute it however you liked across the early universe. You have complete freedom. Every arrangement is on the table. Now shut your eyes and pick one at random. What do you get? You do not get anything resembling what we see. Gravity is an amplifier, and it amplifies the thing it's given. Hand it an uneven distribution, and it makes the unevenness worse. Dense regions pull harder, so they get denser, so they pull harder still. It's a runaway. And when you start from a random arrangement in a universe that dense and that hot, the unevenness isn't subtle. It's savage. Regions collapse almost immediately. Space-time curls up on itself in tangled, violent knots. Black holes form everywhere, at once, in enormous numbers, and they eat everything. That's the typical outcome, not the disaster scenario, the default. Out of all the ways the universe's contents could have been arranged, the overwhelming majority end in gravitational collapse before anything interesting has a chance to happen. No galaxies, no stars, no chemistry, no 13 billion years of anything. A universe of black holes, merging in the dark, and then nothing. A black hole beginning was not one possibility among many. It was the likely one. And this is the point where I need you to let go of the framing you've carried your whole life, because it's been quietly pointed in the wrong direction. The question was never, how did order emerge from chaos? We already went through that. The universe didn't climb out of chaos. It started ordered, and has been falling ever since. So the real question, the one that keeps people awake, is much sharper. Why did the universe avoid the chaos, when chaos was so much easier to make? Here's the version that tends to land. Take a deck of cards, shuffle it properly, really shuffle it, until you've destroyed any trace of the order it came in. Now deal all 52 face up, and find them in perfect sequence, ace through king, suit after suit, exactly the way they came out of the box. You wouldn't call that luck. Nobody would. If that happened at a table you were sitting at, you'd assume something about the shuffle. You'd assume something about the dealer. The one explanation your mind refuses to accept is coincidence. And it refuses because the odds are absurd. 1 in a number with 68 digits in it. Now make it worse in the way the universe makes it worse. You don't get to shuffle again. There's no second hand, no long night at the table, where eventually the improbable shows up. There is one deal. It happened once, 13.8 billion years ago, and everything that has ever existed is sitting on top of the result. And the odds against the arrangement we got are not 1 in a 68-digit number. Roger Penrose, who we're going to be spending a lot of time with, worked out an estimate for how finely tuned the initial state had to be, and the number he arrived at is so large that you cannot write it down. Not because there isn't enough paper, because there aren't enough particles in the observable universe to serve as digits, even if you used 1 atom per digit. The number describing the improbability is bigger than the universe it describes. I'll be careful here, because this is exactly the kind of statement that gets misused. That figure depends on assumptions, on how you count the possible states, on what you take the relevant space of options to be, and serious people argue about all of it. It is an estimate within a framework, not a measured quantity. But the argument about the exact size of the number is an argument between people who all agree it's enormous. Nobody credible is claiming the smoothness was ordinary. That's Anomaly One. The universe was dealt a perfect deck, once, and no one can tell you why. The second anomaly is the asymmetry, and it's subtler, and once you see it, you can't stop seeing it. Here's the strange thing about the laws of physics. Almost none of them care which way time runs. Take Einstein's equations, the ones that govern gravity and the shape of space-time itself. Feed them a situation and let them run forward, and you get a prediction. Now run them backward. Reverse the direction of time in the mathematics, and they work just as well. They're not built with a preference. Neither is Newton's mechanics. Neither is electromagnetism. Neither, for the most part, is quantum theory. Film a planet orbiting a star, and play the film backwards, and nothing looks wrong. Both versions obey the same rules. Physics, at its foundations, is very close to being blind to the difference between past and future. And yet, look at the actual history of this universe, and it is violently, unmistakably one-directional. It began smooth, that near-perfect uniformity we've been circling. And what does gravitational collapse produce at the other end? The interiors of black holes, singularities that are not smooth at all, but grotesque, space-time stretched and squeezed and torn into distortions that make the word shape stop meaning anything. So the beginning and the ending look nothing alike. The beginning is orderly, and the endpoints are monstrous. If the underlying laws don't distinguish past from future, why does cosmic history look like a completely different kind of thing, depending on which end you're standing at? Penrose gave this a name and a form, and it's worth understanding what he actually did, because the honest limitations of it are the whole point. Curvature, the bending of space-time that we experience as gravity, comes in more than one flavor. Part of it is directly tied to the matter sitting there. But there's another part, and this is the part that describes gravity operating freely, on its own. Tidal distortion. The stretching and squeezing a gravitational field does to things falling through it. The part that travels as gravitational waves and doesn't need matter present to exist. Mathematically, it's called the Weyl curvature. And Penrose's proposal, the Weyl Curvature Hypothesis, is beautifully simple to state. At the beginning of the universe, that free gravitational curvature was essentially zero, and there is no rule preventing it from becoming enormous later. So it does. It grows, relentlessly, as matter clumps and collapses, and it runs away toward infinity at the heart of every black hole. Go back to the bedsheet. A sheet pulled tight and flat across a bed is smooth. You can see at a glance that someone arranged it that way. Now sleep on it. Every night it crumples a little more, and it never once uncrumples on its own. The smoothness was the special condition. The crumpling is what happens when you simply let time pass. Penrose's hypothesis says the universe's gravitational field started made, and has been getting slept in ever since. It fits. It explains why the arrow of time points where it does. It ties the beginning of the universe directly to the reason you remember yesterday. It's one of the most elegant ideas in the whole subject. And here's the problem with it, stated as plainly as its own author states it. It's a description, not a mechanism. Nothing in known physics enforces it. There is no law that says the Weyl curvature must vanish at an initial singularity. Penrose didn't derive it from something deeper. He looked at the universe, saw what must have been the case, and wrote it down as a constraint that seems to have been imposed. He has been explicit that it's a hypothesis, and that the physics which would explain it is missing. Something appears to have set that condition at the boundary of time. We don't know what, and we don't have a theory in which it comes out automatically. So Anomaly Two isn't solved. It's been given a precise shape, which is real progress. You can't attack a problem you can't state. But the shape has a hole in the middle. And there's a detail attached to it that I find genuinely unsettling, and I want to leave it with you. Black holes are one way. Things fall in. Nothing comes back out. Take that and reverse it in time. Remember, the equations allow this. and you get the mirror image, an object that things come out of and nothing can go into, a white hole, matter and light pouring outward from a singularity, a past boundary rather than a future one. Einstein's equations permit white holes, they're valid solutions, and we have never seen one, not a hint of one. There's a long-standing suspicion in physics, sometimes framed as a kind of cosmic censorship, that nature simply doesn't allow naked singularities to sit out in the open where anyone can see them. Black hole singularities are decently covered. There's a horizon around them, and whatever horror is happening at the center, it's happening where it can't affect us. The universe, apparently, has the good manners to hide its worst-behaved regions. Except for one. Because the Big Bang, looked at with cold eyes, has an uncomfortable resemblance to exactly the thing we never see. Everything in existence emerging from a singular past boundary. Matter and radiation streaming outward from a condition where the known laws break down. And this one is not hidden. There's no horizon around the beginning of the universe. Nothing shields it. That ancient light we've been discussing, the microwave glow filling every direction, that is a direct line of sight, running backward, toward the place where physics stops working. The initial singularity is naked. It is visible. Its light is arriving in this room right now, and it has been passing through every human being who has ever lived. The one uncensored singularity in the universe is the one we all came out of, and it's pointed at us. That's Anomaly Two. And now the third one, which is the strangest of the three, and I'm going to tell you almost nothing about it. That's deliberate. I need the other pieces in place first, or it won't mean what it should. Here's what I'll say. Several of the most serious attempts to solve the first two anomalies, real theories, from real physicists, built for exactly the right reasons, end up making a prediction about observers, about conscious beings capable of looking at a universe and thinking about it. And the prediction is that beings like us should be vanishingly rare. Not rare compared to nothing, rare compared to something else that the mathematics says should vastly outnumber us, in almost every one of these models, by margins that make the numbers we've already discussed look modest. And if that's right, then the fact that you exist, that you're a person with a coherent past, sitting in a stable world, watching a documentary, holding memories that connect to each other and to a real history, is not just a nice fact about your Tuesday. It's evidence. Against those models, you are the data point that kills them. I'm going to leave it there. I know exactly what I'm doing, and I'd rather earn it than spend it now. When we come back to this, you'll understand why physicists talk about it in the tone they use, which is not the tone of people discussing an interesting puzzle, but of people discussing something they'd prefer not to have found. It's coming. So, 3 things. Hold them in one hand, because everything from here gets measured against them. The smoothness. The universe began in the one arrangement gravity was overwhelmingly unlikely to produce, and no one can say why it was dealt that hand. The asymmetry. The laws don't distinguish past from future, but the universe emphatically does. Smooth at one end, monstrous at the other. And the best description we have of that fact is a hypothesis nobody can derive. The observers, which I'm not explaining yet. Every proposed solution from here on has to survive all 3. Not 1, not 2. And you're going to watch a lot of very good ideas fail that test in interesting ways. Physics has an answer for the first one. A famous, elegant, extremely successful answer. And I want to show you exactly how it works. and then exactly where it doesn't. There is an answer to the first anomaly. It's a good one. I want to be clear about that before I lay a finger on it, because what I'm going to do at the end of this is show you where it breaks, and if you arrive at that moment thinking it was a weak idea all along, you'll have learned nothing. This is not a weak idea. It's one of the most successful proposals in the history of cosmology. It made a prediction that could have killed it and didn't, and the person who came up with it did so while trying to solve an entirely different problem. It's called inflation, and the shape of it is this. Somewhere in the first fraction of the first second, long before atoms, long before nuclei, at a moment so early that the fractions involved stop meaning anything, the universe went through a brief episode of expansion so violent that the word expansion barely covers it. Not the steady, gentle stretching we see today. This was exponential, doubling, and then doubling again, and then again, over and over, in intervals so short that you could fit an enormous number of doublings into a span of time that rounds to zero by any human measure. A region far smaller than a proton was inflated to something larger than a grapefruit, and in cosmological terms that understates it wildly, because from that grapefruit came everything we can see. And then it stopped. The energy driving it dumped itself into ordinary matter and radiation. The universe filled with hot particles, and the more familiar story took over. Cooling, nuclei forming, the fog clearing, the light we've been talking about setting off on its journey. Now, why would anyone propose something so extreme? Because it fixes two things at once, and the way it fixes them is genuinely elegant. Start with the smoothness. Take any patch of space, no matter how wrinkled, no matter how uneven, and stretch it by a factor large enough, and what happens? The wrinkles flatten, not because anything pushed them out, because you're now looking at a tiny fraction of the original surface, blown up to fill your entire field of view. Think about a balloon with a wrinkled, crumpled surface. Inflate it to the size of the Earth. Now stand on it. The patch under your feet, which is all you can see, is flat. Perfectly, boringly flat. The wrinkles still exist somewhere out there, but they've been stretched so far apart that none of them fit inside your horizon anymore. That's the trick. Inflation doesn't remove the unevenness. It expands the scale of the unevenness until it's far larger than anything we could ever observe, and leaves us sitting inside one smooth-looking sliver. And it solves the other problem too, the one I told you to hold on to. Two patches of sky in opposite directions, the same temperature to 5 decimal places, with no possible contact between them. Inflation's answer is beautiful in its simplicity. They were in contact. Before the expansion, the entire region that became our observable universe was small enough that light could cross it easily. Everything had time to mix, to equilibrate, to reach a common temperature, the ordinary way, by contact, the way a hot cup and a cold room reach agreement. And then inflation hurled those regions apart, so far apart that no signal could ever cross between them again. They're not strangers who happen to match. They're old acquaintances who were separated. The uniformity isn't a miracle, it's a memory. That's the horizon problem solved, and the flatness problem solved, from one idea. And here's what elevates it from a clever story to real science. If inflation happened, it should have left fingerprints. Quantum mechanics doesn't allow anything to be perfectly uniform. Even empty space has irreducible fluctuations, tiny ripples in the fields, appearing and vanishing constantly. Under inflation, those microscopic quantum ripples would have been stretched too, blown up from the subatomic scale to the astronomical, frozen into the fabric of the universe as faint variations in density. And you can calculate what pattern they should form. Not just, there should be some ripples, a specific statistical signature, a particular distribution of sizes, a prediction about how much variation you'd find at each scale. That calculation was done before the measurements existed. Then the satellites went up and mapped the ancient light in fine detail, and the pattern of hot and cold spots came back, and it matched. The distribution of fluctuations across that map has the character inflation said it should have, at a level of agreement that has kept improving as the measurements got better rather than falling apart. That is not nothing. That is a theory sticking its neck out and surviving. So the tiny variations that gravity later gripped and grew into every galaxy in the sky, the seeds of all structure, including the specific seed that eventually became the Milky Way, the Sun, this planet, you, those may well be quantum fluctuations from the first instant, magnified beyond recognition and printed permanently across the cosmos. I find that one of the most beautiful ideas anyone has ever had. Everything large began as something too small to see, in a moment too brief to name. Good. Now let's test it. 3 anomalies. All 3, no skipping. And we start with the one inflation was built for. Against the smoothness. Inflation takes a patch and smooths it. Established, tested, works. But look closely at what that sentence requires. It requires a patch. Not just any patch. Inflation doesn't happen spontaneously in arbitrary conditions. It needs a specific field, sitting in a specific energy state, across a region that's already reasonably uniform, already the right size, already not collapsing. The engine has preconditions, and those preconditions are themselves special. So the question doesn't disappear, it changes address. Why was there an inflation-ready region before inflation had smoothed anything? What arranged the pre-inflationary conditions well enough for the smoothing mechanism to switch on? Because if the pre-inflation universe was the wild, lumpy, gravitationally chaotic mess we said a random beginning should be, then most of it would have been collapsing into black holes, rather than politely holding still while a field settled into the right configuration. I want to give you the analogy that made this click for me, and it's not cosmic at all. It's domestic and it's slightly embarrassing. Someone is coming over in 10 minutes, and your house is a disaster, so you do what everyone does. You gather everything, the laundry, the mail, the boxes, the things you have no plan for, and you shove all of it into one closet, and you close the door. Now look at the floor. Spotless, genuinely, verifiably clean. If your guest measures the floor, it passes. Have you reduced the amount of mess in the house? Not by a single item. You've relocated it. You've moved it to a place you've agreed not to look, and the agreement not to look is doing all the work. That's the honest verdict on inflation, and the first anomaly. It explains, with real precision, why the region we can observe looks smooth. It does not explain why there was order available to begin with. It takes the initial conditions problem and pushes it back before inflation started, into a regime we can't see and don't have a theory for. Partial credit. Substantial partial credit. The floor really is clean, and the floor is where we live, but the mess is still in the house. And there's a sharper version of this objection that's worth knowing about, because it's the one that makes theorists uncomfortable rather than merely thoughtful. When people try to count how likely it is that a universe would land in an inflation-ready state, versus simply landing in the smooth state directly, some of those analyses come out badly. The inflating starting point can look less likely than the outcome it was invoked to explain, meaning you've bought your explanation by assuming something even rarer than the thing you were puzzled by. That counting is disputed, and the disputes are technical and unresolved. But it's not a fringe complaint. It's the kind raised by people who take inflation seriously. Against the asymmetry. Second anomaly. Why does the universe look one way at the beginning and a completely different way at the end, when the underlying laws don't distinguish the two directions? Inflation says nothing. I don't mean it says something inadequate. I mean the question isn't in its scope. Inflation is a mechanism for making a region large, flat, and uniform. It's not a statement about why the gravitational entropy of the cosmos was near zero in a fundamental sense, and it doesn't tell you why time has a direction. In fact, and this is subtle but it matters, inflation quietly requires the arrow of time to already exist. The whole story is told in one temporal direction. First, there's a field in a particular state, then it drives expansion, then it decays and reheats the universe. That sequence assumes a before and an after. It uses the very asymmetry it would need to explain. You can't derive the arrow of time from a story told in its terms. Verdict: no answer. Not a wrong answer, not a partial one. Simply silence. Against the observers. And now we open the third one. I told you I was holding it back. Here's why the wait was necessary. The third anomaly doesn't arrive on its own. It arrives as a consequence of the solution to the first. You have to build inflation before you can see what inflation does to you. Because there's a feature of inflation that most versions of it can't easily avoid, and it goes by the name eternal inflation. The reasoning runs like this. Inflation ends when the field driving it decays into ordinary matter. But that decay is a quantum process, and quantum processes are probabilistic. They don't happen everywhere at the same instant. In some regions the field decays, and inflation stops, and a universe like ours emerges. In other regions it hasn't decayed yet, and those regions keep inflating. Now remember how fast inflation expands things. The still inflating regions grow exponentially, far faster than the decayed regions can eat into them. So the inflating volume always wins the race. New pockets keep dropping out, becoming universes, while the space between them keeps stretching. And it never finishes. Not after 1 trillion years, not after any number of years. In eternal inflation, expansion carries on forever, spawning region after region, without end. So you have infinite time and unbounded volume, and that changes what impossible means. In a universe with infinite duration and infinite space, anything with a probability greater than zero happens. Not once, infinitely often. Random fluctuations in the fields, given long enough, will occasionally assemble something ordered purely by chance. Almost always it's trivial. A few particles briefly arranged in a pattern that means nothing, dissolving immediately. But there's no upper limit on what a fluctuation can produce, only a decreasing probability. Wait long enough and something more elaborate appears. Wait absurdly longer, and something more elaborate still. Wait long enough, and disorder will occasionally produce an observer. Not a planet, not a civilization, just the minimum sufficient thing. An isolated, self-aware structure, complete with an internal state that includes memories. Memories of a childhood that never occurred, of a world that was never there, of a documentary about cosmology it never actually watched. Coalescing out of noise, existing for a moment, dissolving back into it. Physicists call these Boltzmann brains. Here's the image that gets it across. Picture an old television tuned to static, random noise, endlessly, meaninglessly. Sit and watch it for an hour, and you'll see nothing but chaos. But every frame is a random draw, which means that with enough frames, an unimaginable number of them, one will by pure chance display something that looks exactly like a face, fully formed, eyes, mouth, expression. Not because anything drew it, because with enough random draws, every arrangement eventually turns up. The face doesn't know it came from static. If the face could think, it would think it was in a photograph. Now here is the problem, and it's not an amusing one. Producing an observer the way our universe did it is enormously expensive. You need a low entropy beginning, 13 billion years of galaxy formation, generations of stars living and dying to forge the heavy elements, a stable planet, chemistry, evolution, the entire lumbering apparatus. And it produces a finite number of observers before the whole thing runs down. Producing an observer by fluctuation is cheap by comparison, because it's not competing with a finite budget. In an eternally inflating space-time, there is no deadline. The fluctuation route keeps producing observers forever. Finite versus forever. So if the model is right, the overwhelming majority of all conscious beings that ever exist are not the products of orderly cosmic histories. They're fluctuations. Brief, isolated, surrounded by disorder, holding memories that correspond to nothing. Which means the typical observer, the one you'd expect to be, if you knew nothing else about yourself, is a fluctuation with fabricated memories in a mostly empty, mostly disordered universe. You are not that. Look at what you actually have. Your memories are coherent. They connect to each other in consistent sequences. They match physical records outside your head, photographs, other people's accounts, objects that carry the marks of the history you remember. You are surrounded by an enormous, structured universe full of galaxies, which is exactly what you'd expect from a long, orderly history, and exactly what a random fluctuation has no reason to produce, because generating a whole cosmos by accident is vastly more improbable than generating just the observer. Every second that passes, and the world stays coherent, is another second of evidence. And that coherence is data. It's a measurement, and it points somewhere unpleasant. If a model predicts that beings like you should be freakishly rare compared to fluctuation observers, and you're demonstrably a being like you, then the model is in trouble. Something is broken, in the way it counts probabilities across infinite volumes, in its boundary conditions, or in the theory itself. This is a live, serious problem in cosmology. It's not a thought experiment people play with at parties. It's a constraint that gets used to rule proposals out. If your model predicts that Boltzmann brains dominate, that's widely treated as a reason to reject the model. And the attempted escapes have their own flavor of strangeness. One line of argument tries to fix the counting by restricting how much of the inflating space-time you're allowed to include, and the version of the universe you're left with, in some of these proposals, has to be finite in a very particular way, cut off by rules that were invented specifically to make the ratio come out right. Another approach requires the inflating region to reach a size so preposterous that the number describing it doesn't function as a quantity anymore. It functions as a warning light. When your solution needs a number that large to work, the honest reading is not that you've solved it. It's that the theory is telling you something. So the tally on inflation, against the lattice. Anomaly 1, partial credit. The mess is in the closet. Anomaly 2, no answer, out of scope. Anomaly 3, actively worse. The solution to the first anomaly generated the third. And there's one more wound to look at before we move on, because it closes off the exit people usually reach for. If inflation goes on forever into the future, the natural thought is, maybe it goes forever backward too. Maybe there was never a beginning at all. Maybe inflation has simply always been happening, with no initial state to explain, and the whole problem of initial conditions dissolves because there were no initial conditions. That escape route was studied carefully, and the result is known by the initials of the three physicists who produced it: Bohr, Guth, and Vilenkin. Guth being the same person who proposed inflation in the first place, which tells you something about how the field actually works. What they showed is a geometric statement, and it's more general than any particular model. If a space-time has been expanding on average, if the average expansion rate along a path traced backward stays positive, then that space-time cannot be extended infinitely into the past. It is, in the technical language, past geodesically incomplete. Follow the histories backward, and they reach a boundary. They stop. The analogy I like is a fuel gauge. Suppose you climb into a car that's been driving, and you check the tank. It's a quarter full, and you know the rate the engine burns fuel. You don't need to know where the journey started, what route it took, or who was driving. You can state with certainty that it has not been driving forever, because if it had, the tank would be empty. The current state contains information about the finitude of the past. Now, and this is the part that gets butchered constantly, so I'm going to be slow about it. Past incomplete does not mean created from nothing. It does not prove a beginning of existence. It does not establish a moment of creation. Vilenkin himself has spent years correcting people who quote the result as though it did. What it establishes is narrower and, honestly, more interesting. The inflationary description cannot be extended infinitely backward. The equations reach a point where they no longer apply. Something else has to take over there, some other physics, some other phase, some other description we don't currently have. That could be a beginning. It could also be a bounce, where a prior contracting phase turned around. It could be a static or near-static era preceding the expansion. There are researchers actively working on exactly these loopholes, examining whether the theorem's assumptions about average expansion, about how space-time is extended, about whether certain paths are the right ones to follow, can be violated in physically sensible ways. That work is ongoing, and the arguments are real. But whichever way it resolves, notice what it doesn't do. None of it removes the problem we started with. Push the boundary backward, insert a bounce, add a prior phase. You still have to explain why the state at that boundary was the astonishingly ordered one that made everything possible. Moving the wall doesn't tell you why there's a painting on it. So the smoothing didn't create the order, it inherited it. Which means the order was written in before the universe had any way to produce it, before there was a mechanism, before there was anything for a mechanism to act on. And some physicists have looked at that and drawn a conclusion that sounds like surrender but isn't. They've stopped asking what caused it and started asking whether it was simply a rule. Watch what happens when a question refuses to move for long enough. Eventually, somebody stops trying to answer it and starts asking whether it was the wrong kind of question. That's the turn we're taking now, and I want you to feel how strange it is before we get into the substance. Every attempt so far has assumed the same thing, that the order at the beginning was produced, that something did it. There was a state, and then a process acted on that state, and the smoothness came out the other end. Inflation is exactly that shape of answer, a mechanism, a machine, a thing that happens to a universe. But there's another possibility, and it's been sitting there the whole time. What if the smoothness wasn't caused by anything? What if it was just the rule? Here's what that means, properly. Physics has always come in two parts, and we tend to only notice one of them. There are the laws of motion, the equations that tell you how a system evolves from one moment to the next. Give me the state of something now, and the laws will tell you the state of it later. That's the part everyone thinks of as physics. But equations of motion are useless on their own. They're machines that transform one state into another, and they will sit there doing nothing until you feed them something to transform. You have to hand them a starting condition, and that starting condition has never been part of the laws. It's always been an input, something you go out and measure, an accident of history that the equations accept without comment. The proposal is that for the universe as a whole, that stopped being true. That there is a law about initial conditions, not a mechanism that generated them, not a process that shaped them, a restriction on what a beginning is permitted to be, standing alongside the laws of motion rather than derived from them. A rule of the same fundamental status, doing a different job. Roger Penrose made that proposal specific, and the specificity is what makes it worth taking seriously rather than dismissing as a shrug in formal dress. To see it, we need to look properly at curvature, because it isn't one thing. When space-time bends, the bending has parts, and the parts do different work. One part is chained directly to the matter and energy sitting in that region. Put mass somewhere, and space-time curves there in a way that's completely determined by how much you put and how it's arranged. That part of curvature has no independence. It's a response. Take the matter away, and it vanishes instantly, because it was never anything more than the geometry's reaction to being told what to do. Then there's the other part. This is gravity acting on its own account. It's the tidal effect. The fact that if you fell toward a massive object, the parts of you nearer to it would be pulled harder than the parts further away, and you'd be stretched along one axis and squeezed along the others. Nothing needs to be present at your location for that to happen to you. The distortion is a property of the region itself, and it's the part that can travel. Gravitational waves, real, detected, measured, ripples in the shape of space-time crossing the universe from collisions that happened before there was an Earth, are made entirely of this free curvature. They carry no matter. They're pure geometry, propagating on its own, arriving here and stretching the planet by less than the width of a proton as they pass through. That's the Weyl curvature, the structure gravity has when nothing is telling it what shape to take. Now, Penrose's hypothesis in one sentence. At the initial singularity, that free curvature was constrained to essentially zero. At final singularities, the ones inside black holes, the endpoints of collapse, it is not constrained at all, and it runs away without limit. One rule, applied at one end of time and not the other. Think about what an odd sort of law that is. It doesn't tell anything how to behave. It doesn't govern a process. It simply declares that one boundary of time is subject to a restriction, the other boundary isn't. The past is disciplined. The future is free. And if that's true, If that single asymmetry really is written into the structure of things, then look at what falls out of it. The arrow of time. Not as a separate fact about the universe, not as an extra ingredient, as a consequence. Because if gravitational freedom starts at zero and has nowhere to go but up, then the universe has a direction built into it at the level of geometry, and everything downstream inherits that direction. Your coffee cools and never reheats because of it. The shattered cup stays shattered because of it. Your body ages in one direction. You remember what happened this morning and not what will happen tonight. And that asymmetry in your own head, the most basic feature of being a conscious thing moving through time, traces back, through an unbroken chain, to a constraint on the free curvature of space-time at a boundary 13.8 billion years behind you. Everything that has ever happened to you happened in one direction because of a rule about the shape of the beginning. That's an extraordinary claim to be able to make, and it's not mysticism. It's a real hypothesis with a precise mathematical statement, made by one of the most serious geometers ever to work on gravity. So let's test it. 3 anomalies, no skipping, against the asymmetry. This is its home ground, and it performs superbly. The whole puzzle was that the laws don't distinguish past from future, while the universe emphatically does. Penrose's answer is to locate that distinction precisely, not in the laws of motion, which really are indifferent, but in a separate constraint that applies at one temporal boundary and not the other. The equations stay time-symmetric. The asymmetry lives in the boundary condition. That's a clean division of labor. And it puts the arrow of time somewhere it can actually be discussed, rather than gestured at. More than that, it makes the smooth beginning and the monstrous endings into 2 faces of a single statement, rather than 2 unrelated observations. The reason black hole interiors look nothing like the early universe is that the constraint was lifted. Full marks for description. Genuinely, this is the best account anyone has of why the 2 ends of cosmic history look like different species of thing. Against the smoothness. And here it collapses, and I'm going to be blunt about how it collapses, because the temptation is to let the sophistication of the mathematics obscure something simple. Say it out loud. The Weyl curvature was constrained to near zero at the initial singularity. Now say the other thing. The universe began smooth. Those are the same sentence. The first one is enormously more precise. It specifies exactly which component of curvature, at exactly which boundary, in language that can be written down and manipulated and connected to other results. That precision is worth a great deal. You cannot attack a problem you can't state, and Penrose stated it. But precision is not explanation. Restating the anomaly in exact terms tells you what happened. It doesn't tell you why. And Penrose knows this. He has never claimed otherwise. He has been consistently, unusually clear that this is a hypothesis, a condition the universe appears to have obeyed, written down as a proposal, waiting for a deeper theory to explain it. He has argued, for decades and against considerable resistance, that the missing theory is the one that would unify gravity with quantum mechanics, and that when we have it, this constraint might emerge naturally rather than being imposed by hand. Might. That theory does not exist. So the honest status is this. We have a rule that appears to have been obeyed. We have no law from which it follows, no mechanism that would enforce it, and no physical process that would have imposed it. Nothing in any established framework says the free curvature must vanish at an initial singularity. It simply seems to have. It's a rule with no enforcer. And that's a peculiar object to have found at the foundation of physics. Every other rule we know has something underneath it. A symmetry, a conservation law, a deeper principle it descends from. This one just stands there, apparently true, apparently fundamental, and completely unsupported from below. Against the observers. Neutral, and I'll be brief because there's nothing dramatic to report. The Weyl Curvature Hypothesis doesn't generate the Boltzmann brain problem. It isn't a theory of eternally inflating volumes. It doesn't require infinite spacetime. And it doesn't produce a probability measure that goes wrong. That's a real advantage over the previous section. But it doesn't dissolve the problem either. It says nothing about what happens in the far future. Nothing about whether fluctuation observers eventually arise in a universe left running long enough. Nothing about how you'd count them. Anomaly 3 passes straight through it without interacting. So, one full mark, one restatement, one abstention. Which is better than the last scorecard, and still not a solution. Now I want to take you somewhere darker, because there's a detail I left with you earlier, and it's time to press on it. The white hole. Remember the structure. A black hole is a one-way door pointing inward. Things cross the horizon, and nothing returns. Not matter, not light, not information in any form we can retrieve. It's the most complete kind of one-directionality nature offers. And the equations of general relativity don't care about direction. So the mirror image is also a valid solution. Reverse it in time, and you get an object with the same geometry running the other way. A boundary that things pour out of, and that nothing can enter. Matter and radiation streaming outward from a singularity that lies in the past, rather than the future. Einstein's equations permit these. They're not exotic add-ons or speculative modifications. They fall out of the same mathematics, with the same legitimacy as the black holes we've now photographed. And we have never seen one. Not a candidate. Not an ambiguous signal. Nothing. There's a long-standing suspicion in the field about why, and it goes under the name of cosmic censorship. The idea is that nature does not permit naked singularities, places where the known laws break down sitting out in the open where their breakdown could reach us. Black hole singularities are, in this reading, decently covered. Whatever is happening at the center is happening behind a horizon, sealed off, unable to affect anything outside. The universe apparently has standards about where it does its worst behavior. It's never been proven. It's a conjecture, and a famously stubborn one. But it captures something the universe seems to respect. Except once. Because look at what the beginning actually is, structurally, with the associations stripped off. Everything that exists emerging outward from a singular past boundary, matter and radiation streaming away from a condition where the known equations stop functioning. Things came out. Nothing went in. There was no in, no earlier region, no exterior from which anything could have entered. That is the geometry of a white hole. Not a metaphor for one. The same structure. And this one was never hidden. There is no horizon around the beginning of the universe. Nothing shields it from view. That ancient microwave glow we spent a whole section establishing, the oldest light there is, arriving from every direction, passing through this room and through your body while you listen, is a direct line of sight running backward toward the boundary where physics fails. Not an inference about it, a view of the region as close to it as light can carry. The one uncensored singularity in the cosmos is the one everything came out of, and it is pointed at us permanently, and it has been shining on every human being who has ever lived. Now, what do we make of that resemblance? I'm going to give you both readings, and I'm not going to pick, because I don't think the honest position is to pick. The first reading is that it's a genuine structural clue, that the similarity is telling us something real about the character of the initial state, that whatever the beginning was, it belongs to the same family of objects as the endpoints of collapse, related to them by the reversal the equations permit. On this reading, the reason we see no white holes anywhere else is that there's exactly one. It's not an object inside the universe, and we are downstream of it. It doesn't sit in space. It's the boundary of all of it. The second reading is more deflationary, and quite possibly correct. It's that this is what you get when you run equations backward, past the point where they still describe anything. General relativity is a classical theory. It assumes space-time is smooth and continuous. As you approach the initial boundary, densities climb without limit, and quantum effects on the geometry stop being negligible. And in that regime, the theory is being used far outside its established domain. Following its solutions back there, and taking the resulting shape seriously, might be no more meaningful than extrapolating a weather forecast 1,000 years out. The equation still produces an answer. The answer stopped meaning anything a long way back. Both readings are defensible. Both are held by serious people. The resemblance may be a clue, or it may be an artifact, and there is currently no way to settle it, because settling it would require the theory that doesn't exist yet. Here's the analogy I keep returning to, and it's a kitchen. Water goes down a drain. It swirls, it narrows, it disappears, and it does not come back up. That's a one-way geometry, and you've watched it 1,000 times without thinking about it. A tap is the identical geometry running the other way. Water emerging from a place you can't see into, flowing outward, and nothing goes back up the pipe. Every drain in the universe, we've found. Millions of them, in every galaxy we look at, some of them monstrous. We have found exactly one tap. It was left running once, at the beginning, and everything, every galaxy, every atom, every thought anyone has ever had, is what came out of it. And now let me name the trap, because I think you can feel the shape of it already. Every route we've taken has ended in the same place. Inflation smooths the observable universe and hands the initial conditions problem backward to a pre-inflationary regime it can't describe. Push past inflation, and the geometry says the description can't be extended infinitely backward. You reach a boundary, and something else has to take over, and nobody knows what. Penrose names the constraint at that boundary with beautiful precision, and tells you honestly that no known law enforces it. The white hole resemblance offers a clue that may only be the residue of equations applied where they no longer apply. 4 different roads, one wall, and it's the same wall each time. A moment where the equations stop describing and start merely pointing. So let me tell you what's actually happening at that wall, because the word we use for it is one of the most misunderstood in all of science. The singularity. People hear it and picture a place, a point, something you could in principle travel to, infinitely small and infinitely dense, sitting at the start of time like a location on a map, with the first moment inside it. It isn't a place. What actually happens, mathematically, is that as you trace the equations backward, certain quantities climb without limit. Density, temperature, curvature, and they don't level off at some enormous value. They head toward infinity, and the expressions describing them start dividing by zero. Infinity is not a measurement. You cannot measure infinite density, because infinity isn't a number that could show up on an instrument. When infinity appears in your output, you have not discovered an infinite thing in the world. You have discovered that your equations have been pushed somewhere they no longer function. This has happened before, and physics recovered every time. Equations describing fluids blow up in ways that just signal the fluid description failing. You switch to molecules and the infinity vanishes. Early quantum electrodynamics produced infinities that turned out to reflect the theory being used beyond its range. Infinities in physics are almost never discoveries. They're almost always error messages. So the singularity at the beginning of the universe is probably not a thing that existed. It is the sound of general relativity failing, the point where a theory that has been spectacularly successful for a century announces that it has reached the edge of its own competence and stopped meaning anything, which is a strange kind of relief and a strange kind of horror at once. Relief, because the infinite density at the start of time is likely a phantom, an artifact of the wrong description rather than a real condition. Horror, because the entire question we've been chasing, where the order came from, lives on the other side of an equation that no longer works. We haven't been failing to answer the question. We've been failing to reach it. Which raises a possibility that sounds like a dodge until you see the mathematics. What if there is no edge to explain, because the universe doesn't have one? Every attempt so far has treated the beginning as a thing to be explained. There's a boundary. Something happened at it, or something was true of it, or some condition was imposed on it. And the job of physics is to work out what. That's the assumption underneath inflation, underneath Penrose, underneath every road we've walked down. There is an edge, and we need an account of the edge. The next idea does something else entirely. It doesn't explain the edge, it gets rid of it. And I want to be careful with the word "gets rid of," because that sounds like evasion, like someone dissolving an inconvenient question by refusing to answer it. It isn't that. This is a specific mathematical proposal made by James Hartle and Stephen Hawking, and it contains what I think is the single most elegant idea in this entire film. Here's the problem it was built to solve. We ended the last section with the singularity being an error message rather than a discovery. General relativity fails there. It has to fail there. It's a classical theory, and at the density and curvature involved, quantum mechanics cannot be ignored. Everybody agrees on that much. But agreeing that gravity must be quantum is not the same as knowing how. A full theory of quantum gravity doesn't exist. So the question becomes, can you say anything sensible about the origin of the universe using the quantum tools we do have, without waiting for the theory nobody has finished? Hartle and Hawking's answer was yes, and it starts with something quantum mechanics has always done. In ordinary quantum theory, a particle traveling from one place to another doesn't take a path, it takes all of them. Every conceivable route, direct, absurd, looping out beyond the galaxy and back, contributes to the outcome, and you calculate what actually happens by adding up the contributions from every possible history. Most cancel each other out. What survives is what you observe. This isn't interpretation. It's how the calculations are done, and they work to extraordinary precision. Now make the leap. Instead of summing over the possible paths of a particle, sum over the possible shapes of space-time itself. Every geometry the universe could have, every way the fabric could be curved and connected, contributes to the state of the cosmos. That's quantum cosmology. And it changes what the question even is. You're no longer asking what the universe was doing at some early instant. You're asking about a wave function for the whole thing, which raises an immediate problem, and it's the same problem in a new suit. When you calculate a wave function in ordinary quantum mechanics, you have to specify conditions at the edges of the region you're working in. Boundary conditions. And for the universe, that means specifying something about the boundary in the past, which is exactly the thing we can't explain. So Hartle and Hawking proposed the most economical possible answer to that question. There is no boundary. Not that the boundary is smooth or special or subject to a rule. That it does not exist. The condition on the universe's past edge is that it doesn't have one. Now, how can something have a finite past and no earliest edge? Those sound contradictory. And this is where the geometry does something genuinely beautiful. Near the origin, in this proposal, the distinction between time and space breaks down. Time as you experience it is different from space in a way that's not just psychological. It's built into the mathematics of relativity. Time enters the equations with an opposite sign to the spatial directions. That sign difference is why you can move freely through space and only forward through time, why there's a difference between here and now. The proposal is that as you approach the origin, that difference stops holding. The temporal direction becomes, in the mathematics, more like another spatial one. And a geometry with no special time direction has no earliest moment. For the same reason a sphere has no leftmost point. There's nothing to be earliest than. So the sharp point at the start of time gets replaced by something smoothly rounded. The universe doesn't begin at an edge. It closes off. The image Hawking used for the rest of his life is the best one anybody has found. Ask what lies further south than the South Pole. It's a perfectly good English sentence. Every word is legitimate, the grammar is impeccable, and it has the shape of a question that deserves an answer. Stand at the pole and you can point in a direction and ask what's over there. That works everywhere else on Earth. But at that specific point, south has run out. Not because there's a wall, not because something blocks you, and not because we haven't explored it yet. Because the concept has no referent there. Every direction from the pole is north. The question is malformed, and it took you standing at the pole to notice. Nothing dramatic happens when you arrive. There's no boundary, no edge, no barrier. The surface is perfectly ordinary, smooth, continuous, unremarkable. Southness simply stops applying. That's the claim about time. Before the Big Bang is a sentence built out of good words that stops referring to anything as you approach the origin. And the reason nobody can tell you what came before isn't that the answer is hidden. It's that the question dissolves. Try it with your hands. Run a finger down the inside of a mixing bowl, starting at the rim, down the wall, and the wall curves, and it keeps curving, and at some point you're moving across the base instead of down the side. And you cannot identify the moment you crossed. There was no line, there was no edge. The curvature just changed continuously until down stopped being available, and you had reached the bottom without ever encountering a boundary. The bowl has a lowest point. It has no bottom edge. Both are true. That's what the no-boundary proposal says the beginning of time looks like. And I want to make sure the force of this lands, because it's easy to hear as wordplay. It isn't wordplay. It converts an unanswerable question into a malformed one. Those are entirely different situations. An unanswerable question is a hole in your knowledge. Something is true, and you can't determine what. A malformed question is a defect in the asking, and the correct response is to notice the defect and stop. And it does this with actual mathematics. Hartle and Hawking wrote down a specific formula, a sum over geometries with a particular restriction on which ones count, namely the ones that close off smoothly with no boundary. And from it, you can compute things. You can extract a probability distribution over possible universes. You can ask what kind of cosmos this proposal predicts. That's the difference between a philosophical move and a physical one. You can check it. So let's check it. 3 anomalies. No skipping. Against the smoothness. This is real progress, and I want to give it full weight. Every previous approach treated the initial state as an input, a fact you go out and measure, unexplained by the theory. Inflation needs a suitable patch and doesn't say where it came from. Penrose names a constraint and tells you honestly that nothing enforces it. The no-boundary proposal doesn't take the initial state as an input. It derives one. Specify the rule. Sum over geometries that close off smoothly. And a particular quantum state comes out. Not an arbitrary state. Not one chosen to fit. The specific state that follows from the condition. And the state it selects is one that tends to favor a smooth, uniform beginning. The special initial condition stops being a coincidence and becomes a consequence. That's the thing everyone has been trying to achieve, and this is the closest anybody has come to achieving it with mathematics rather than assertion. So, genuine progress, not a restatement, an actual derivation. Now the limitation, and it's severe, and I'm not going to soften it. Look at what the derivation required you to have already. It required a wave function, the concept, the framework, quantum mechanics itself, in force before there was a universe for it to be in force in. It required laws of physics, a specific action, particular fields, a set of rules governing how geometries contribute. It required mathematical structure to exist, the whole apparatus of spaces and sums and manifolds. And it required a rule for how to do the summing, which geometries count, how they're weighted, what smoothly closing off means precisely. That last one isn't a technicality. There's more than one way to perform that sum, and different reasonable choices give different answers, including a rival proposal from Vilenkin that uses a different condition and predicts something different. The choice matters, and nothing in the framework tells you which choice is correct. So the universe no longer needs a boundary, but it needs a rulebook. And nothing explains the rulebook. Why that wave function? Why those laws? Why is the sum performed one way rather than another? The proposal removes the edge and hands you, in its place, a set of mathematical structures that were apparently in force before anything existed, and offers no account of why they were the ones in force. The mess went into a smaller closet, a much smaller, much more elegant, mathematically respectable closet. It is still a closet. Against the asymmetry. Second anomaly, and here it's quiet again. The no-boundary proposal is about the past boundary. That's the whole design. It says nothing about the singularities inside black holes, the ones where free curvature runs away without limit, the ones that look nothing like the beginning. So the asymmetry survives untouched. Why should the past boundary round off smoothly while future endpoints are savage? Nothing in the proposal answers that. The condition is imposed at one end because that's where the problem was, not because something explains the difference between the ends. You could argue this is worse than silence, in one narrow sense. Penrose at least stated the asymmetry as a hypothesis, put it on the table, made it something you could argue about. This approach smooths one boundary and leaves the question of why the other end is different entirely outside the frame. Verdict: no mechanism. Against the observers. And here is where it takes real damage, and where all this lattice building finally earns what it cost. Remember, the no-boundary proposal doesn't just say the universe has no edge. It produces a probability distribution. It tells you which universes are more likely. So people did the obvious thing. They asked it what kind of universe to expect. And in the traditional versions of the calculation, the answer came back badly. The proposal tends to favor histories with very little inflation, barely any expansion at all, which means the tiny density variations never get amplified into anything. No seeds for gravity to grip, no clumping. No galaxies, no stars, no heavy elements, no planets. What it favors is a universe that is smooth, sparse, nearly empty, and permanently featureless. A cosmos where nothing ever assembles into anything and nothing is ever around to notice. Read that again with the third anomaly in mind. The theory built to explain the beginning of our universe appears to prefer a universe that isn't ours. And the evidence against it is, once more, you. You exist. You're made of heavy elements forged inside stars, that formed from clumps that grew from those tiny primordial variations. Every structure in your body is a receipt from a history the calculation says should have been unlikely. The galaxies are there. The stars are there. You're watching this. The universe we're standing in is, on this measure, an improbable one. And when your theory assigns low probability to the only data point you have, that's not a footnote. That's the theory failing its test. Now, honesty, because this is contested, and I'd be misleading you if I presented it as a verdict. This objection has been alive since the earliest days of the proposal, and it has never been settled. Hawking and Hartle argued that the calculation is being done wrong, that you have to account for the fact that only observers can ask the question, which changes which histories you should be weighting. Others have argued the whole approach to conditioning on observers is illegitimate. There's a long-running technical dispute about how the sum should be performed, whether certain contributions are being handled correctly, and whether alternative formulations avoid the problem. Some versions of the calculation give different results. Hawking was working on aspects of this in the final years of his life. So it isn't a knockout. It's an unresolved wound that has been bleeding for 4 decades, and the people arguing about it are not amateurs. But notice something about the shape of the objection, because it's the 3rd time we've seen it. Inflation ran into trouble over observers. This runs into trouble over observers. In both cases, the theory produces a distribution, and the distribution says, beings like you should be rare, and you are inconveniently here. The 3rd anomaly keeps arriving uninvited. It's not a topic anyone chose to work on. It shows up as a symptom, on its own, at the end of the mathematics, which is exactly what you'd expect from a genuine constraint, rather than a philosophical preoccupation. Now step back with me, because this is the moment the whole structure pays off, and I want you to see the pattern, rather than just the individual failures. 4 attempts, 4 serious ones, by extraordinary people. Inflation took the order and moved it, smoothed the region we can see, by requiring a pre-inflationary patch that was already special enough to start. The Weyl Curvature Hypothesis named the order with real precision, and admitted, in its author's own words, that no known law enforces the rule. The no-boundary proposal removed the edge the order was written on, and kept the entire rulebook that made the removal possible. And underneath all three sits the same structure. Every one of them requires something already in place before the universe. Inflation needs a field in a particular state. Penrose needs a law about boundary conditions that stands outside the laws of motion. Hartle and Hawking need quantum mechanics, an action, and a rule for summing over geometries. Every explanation of the beginning starts by assuming an ordered framework that was somehow already operating. Nobody has explained the inheritance. They have argued, brilliantly and productively, and with real technical progress, about which closet it's in. And I don't say that to belittle any of it. The work is magnificent. Inflation predicted a fluctuation pattern that turned up in the data. Penrose gave the arrow of time a mathematical home. Hartle and Hawking showed you could calculate about the origin of the universe at all, which nobody had thought possible. These are not failures of intelligence or effort. They're something more interesting. They're a pattern, and patterns that persistent usually mean the problem isn't where everyone is looking, which leaves exactly one direction nobody wants to take. Nobody wants it because it costs the most. Every idea so far has kept something safe, something not up for negotiation, some part of the picture treated as furniture rather than as a question. Each theory paid with a different currency, and each one refused to pay with the same coin. There is one more idea. It is the strangest thing in this entire film, and it works by removing something you have never once considered removing. Here is the thing. Every previous idea kept safe. Inflation gave up on the beginning being calm, and let it be violent instead. Penrose gave up on deriving the smoothness, and proposed it as a law. Hartle and Hawking gave up on the edge of time, and rounded it off. Each one surrendered something, but all four kept the same piece of furniture standing in the middle of the room, untouched, unquestioned, so obviously necessary that nobody thought to ask whether it belonged there. Time. Every one of those approaches assumed that time exists, that there is a sequence, that the universe was in one state and then another, that something came first and something followed, that the word beginning refers to a real feature of reality rather than a habit of thought. The last idea in this film gives that up. And I need to tell you where it comes from, because it wasn't a philosophical stunt. Nobody sat down intending to abolish time. It came out of doing the most straightforward thing imaginable, the obvious next step, taken by people who expected an ordinary answer. Here's the step. Quantum mechanics has a central equation. It describes how the quantum state of a system changes as time passes. Feed it a system, and it tells you what that system does next. It's one of the most successful pieces of mathematics ever written, underneath the behavior of atoms, molecules, semiconductors, everything. But it's always applied to a part of the world, an electron, an atom, a molecule in a laboratory. You draw a box around the system you care about, and everything outside the box, including the clock on the wall, is the environment. The equation describes the inside relative to the outside. So somebody asked the natural question, what if you don't draw the box? What if you apply quantum mechanics to everything at once? The entire universe, all of it, matter and radiation, and the geometry of space-time itself, with nothing left outside. John Wheeler and Bryce DeWitt did the work, and out of it came an equation that bears both their names. It is the most ambitious object in physics, an attempt to write down the quantum state of the whole cosmos in a single line. And when they looked at what they'd derived, there was something missing. There is no time in it. I want to be precise, because this gets garbled. It isn't that time appears in some strange or modified form. It isn't that time is hidden inside a variable with a different name. The variable that would represent time, the thing that appears in every other equation in physics, ticking along and driving the change, is absent. It cancelled out. What's left doesn't read as a description of something evolving. It reads as a constraint, a statement that the universe's quantum state must satisfy a certain condition. Full stop. Not changes according to, not develops into, just is like this. The equation that describes the entire universe describes something that does not happen. It simply is. Sit with that for a moment, because I've been building toward it for an hour and I don't want it to pass in a sentence. We have spent this entire film asking about the beginning of time, why the universe started ordered, what the initial state was, what came before. Every question has taken the form of what happened, and when, and in what order. And the most complete description physics has managed to write down for the universe as a whole doesn't contain a when. There is no external clock. There couldn't be. A clock outside the universe would be part of the universe, and then you'd have to include it and start over. There is nothing to measure duration against, nothing evolving relative to anything else, just a state, satisfying a condition, timelessly. Physicists call this the problem of time, and it took years to accept as a real feature rather than a mistake somewhere in the derivation. People went looking for the error. There wasn't one. When you take quantum mechanics and general relativity and combine them at the scale of everything, time falls out of the mathematics. Here's the way I've found to hold it. Think about a film on a disc. The whole movie is on there. Every frame, the opening and the ending and everything between, all present simultaneously, encoded in a physical object you can hold in your hand. And nothing on that disc is moving. There is no motion in the object. The chase scene isn't happening. The final line isn't being spoken. It's all just there, at once, static. Now play it. Suddenly there's sequence, and momentum, and one moment following another, and a character who doesn't yet know what's coming. But none of that is in the disc. It's in the playback. The experience of one frame following another is something that happens to a viewer moving through the material in a particular order, not a property of the material itself. The disc has no first moment in any meaningful sense. It has a first frame, which is just the one at a particular position in the encoding. And here's the question that turns this from a nice image into vertigo. What if the universe is the disc and not the playback? What if the entire history of everything, the early smoothness, the first stars, this conversation, whatever comes after, exists as a single timeless structure, and the flow you feel, the vivid, unstoppable sense of moving from one moment into the next, is not a feature of reality, but a feature of being inside it? That's not an idle question. It's what the mathematics appears to be saying, and the people who work on this take it seriously enough to have spent decades trying to understand how it could possibly be reconciled with the most obvious fact of your existence, which is that time very clearly does pass, and you are very clearly experiencing it right now. So how do you get playback out of a static object? The most developed answer is that time is emergent, not fundamental, not part of the basic furniture, but something that arises from the relationships between parts of the universe. Here's the reasoning, and it's cleverer than it first sounds. Take the timeless state of everything and divide it, conceptually, into two pieces. Call one piece the clock and the other piece the rest. Now, within that single unchanging total state, there are correlations between the two pieces. When the clock part is in this configuration, the rest is in that configuration. When the clock is in another configuration, the rest correlates with a different one. Nothing is moving. The correlations just exist, all of them, in the frozen whole. But if you're a subsystem inside that structure, if you're part of the rest, with a record-keeping apparatus that correlates with the clock, then what you experience is exactly what you'd experience if time were passing. You find yourself in a state that includes memories, and those memories correlate with earlier clock configurations, and the whole thing hangs together as a sequence. Time isn't a stage the universe stands on. It's a relationship between things inside it. Duration is what correlation feels like from the inside. And under that reading, look at what happens to the question we've been chasing all film. What happened before the Big Bang? It isn't a hard question. It isn't an unanswerable one. It's a question that assumes the existence of something the equation says was never there in the first place. Before requires time to be fundamental, a background against which things are ordered. If time is emergent, arising from correlations within a structure that has no clock of its own, then asking what preceded the whole structure is asking for a relationship to something outside the only thing there is. It's the South Pole again, but deeper. Hawking's version removed the edge of time. This one questions whether the thing that had an edge was ever there. Right. 3 anomalies. One last time, and then we'll step back and look at all of it together. Against the smoothness. This does something genuinely different, and it's worth appreciating before we get to what it fails at. Every other approach treated the early smoothness as an event, something that had a cause, or a condition imposed on it, or a mechanism that produced it. All of those framings assume the smoothness was a state the universe was in at a particular moment, which requires moments. In a timeless framework, that's not what it is. The smoothness becomes a property of the universe's total quantum state, a feature of the whole structure, not a condition at one end of it. Asking what caused it stops making sense in the same way, because causation is a temporal relation, and there's no temporal relation available at that level. That's a real reframe. It doesn't dodge the question, it changes what kind of thing the question is about. But it doesn't tell you why that state. The universe's quantum state has a particular character, one that includes a smooth, low gravitational entropy region and correlations that add up to 13 billion years of history. There are other states it could have had. Nothing in the framework says why this one. And the honest limitation is worse than that, and I'm going to state it plainly because this idea attracts a lot of loose talk. The Wheeler-DeWitt equation is notoriously difficult to define rigorously. It's formally beautiful and mathematically treacherous. There are long-standing problems with making the operators well-defined, with what the solutions even mean, with how you'd extract a probability from a state that doesn't evolve. There is no consensus on its interpretation. Different serious researchers give substantially different accounts of what it's telling us. And some think the whole formulation signals that we're missing something, rather than that we've found something. So this is not a finished theory being applied. It's a frontier with a lot of argument on it. Treat anyone who tells you the universe is definitely timeless with the same caution you'd give anyone who tells you it definitely isn't. Partial credit. A reframe worth having, resting on foundations still being poured. Against the asymmetry. And here, for the first time in this entire film, I get to tell you about something genuinely promising. The arrow of time has been an add-on in every approach so far. The laws don't distinguish past from future, so the asymmetry has to be imported from somewhere. A boundary condition, a hypothesis, a special initial state. Something extra, bolted on to explain why the universe has a direction when the equations don't. But if time is emergent, if it arises from the correlation structure of a timeless state, then the arrow doesn't have to be added afterwards. It could emerge along with time, from the same source. The reasoning goes like this. If the total state is asymmetric in the right way, if the correlations are lopsided, running strongly in one direction and weakly in the other, then any subsystem embedded in it will experience a directed time, because the records it has access to will be correlated with one side and not the other. The asymmetry of the state becomes the asymmetry of experience. Not two facts requiring two explanations. One structural feature showing up as both. That would be a genuine unification. The passage of time and its direction, coming out of the same thing rather than being separately assumed. I want to be careful about how much I'm claiming. This is a direction of research, not a result. It says the asymmetry might have a single origin. It doesn't yet say why the state is asymmetric in the first place. The problem hasn't been solved. It's been shown a promising place to look. But it's the only place in this film where two of our anomalies might collapse into one. That's worth something. Against the observers. And now the third one, which I've been carrying since the opening, and which is where all of this comes to rest. Here's what I want you to notice about the pattern. Inflation failed the observer test. Eternal inflation produces fluctuation observers in unbounded numbers, and the coherence of your world argues against it. The no-boundary proposal ran into the same wall from a different direction, a calculation that favors a nearly empty universe with no structure and nobody in it. Two completely different theories, built by different people for different reasons, using different mathematics. They fail the same way. Both make a prediction about how common beings like you should be. Both come back with an answer that says, rare, absurdly, statistically negligibly rare compared to something else. And in both cases, the refutation is the same, and it is the strangest form of evidence in science. You, not you as a philosophical abstraction, you, specifically, with a coherent history you can inspect. You remember a past, not a vague impression, a structured sequence of events that connects to itself, that has causes leading to effects, that doesn't contradict itself when you examine it closely. The evidence around you is consistent with that past. There are photographs. Other people remember the same events. Objects show wear consistent with the ages you'd assign them. Records agree with records. Written documents from centuries ago describe a world that left physical traces we can still find, and the traces match the documents. And the universe you're in is full of galaxies. It has structure at every scale. Clusters, filaments, stars, planets, chemistry complex enough to build a nervous system. That structure is a receipt from a long, orderly history. It's what you'd expect if the past you remember actually occurred, and it's the last thing you'd expect from a random fluctuation, because generating a whole cosmos of galaxies by chance is vastly harder than generating just an observer who thinks there are galaxies. Every one of those observations is data, ordinary, checkable, physical data. And it has already been used to rule things out. This isn't a speculative exercise. When a cosmological model predicts that typical observers should be incoherent fluctuations, that prediction is tested against the fact that we are not, and models have been rejected on those grounds. Your own coherence functions as a measurement. Think about how peculiar that is. In every other part of science, the observer is supposed to step back, to remove themselves from the experiment, to measure the world without being part of the reading. Here, you are the instrument and the result. The fact that you can follow this argument at all, that your thoughts connect to each other, that you have a stable enough existence to hold a question in your head for an hour, that is the evidence. You are not typical, in the sense several theories predicted you should be, and your untypicality is one of the sharpest constraints we have. That's why I held this back. It's not a curiosity. It's the test that keeps killing otherwise beautiful ideas, and it arrives uninvited, at the end of the mathematics, whether anyone wanted it there or not. Now let me pull all of it together, because we've reached the point where the individual answers matter less than what they have in common. Line them up. 5 approaches. Inflation. A brief episode of violent expansion that smooths whatever region it acts on. Requires a suitable pre-inflationary patch. Move the order backward. Eternal inflation. The natural extension producing endless universes forever. Generates the observer catastrophe. The Weyl Curvature Hypothesis. A precise constraint on free gravitational curvature at the initial boundary. Names the order beautifully. No known law enforces it. The no-boundary proposal removes the past edge entirely, replacing the singular point with rounded quantum geometry. Derives a state rather than assuming one, and needs an entire rulebook to do it. Timeless quantum cosmology. Questions whether the beginning was ever a moment. Reframes the problem, on foundations still under construction. 5 roads. And underneath every single one of them, the same missing thing. The laws of physics tell you how a system evolves once you have given it a starting state. Every equation in the entire subject has that shape. Hand me a configuration, and I'll tell you what happens next, and next, and next, with staggering accuracy. We can predict eclipses centuries ahead and locate spacecraft across the solar system to within meters. But not one of those laws tells you which starting states are allowed. They are completely silent on it. Feed general relativity a smooth universe, and it will evolve it faithfully. Feed it a chaotic one, riddled with black holes, and it will evolve that just as faithfully, with no complaint, no preference, no indication that one is more legitimate than the other. The equations accept whatever you hand them. Here's the cleanest way I can put it. Physics has given us a superb recipe, and absolutely no information about what was in the fridge. The recipe is magnificent, precise, tested, reliable, telling you exactly what happens when you combine these ingredients under these conditions for this long. It has never let us down. And it says nothing whatsoever about why those particular ingredients were on the shelf. It doesn't know. It was never designed to know. The recipe describes transformation, and the question of what was there to be transformed is simply not the kind of thing a recipe addresses. which suggests something that has been circling this entire film without landing. Maybe a complete theory requires a genuinely separate law, not another equation of motion. We have plenty of those and they work fine. Something of a different kind entirely. A law of initial conditions, specifying which quantum state, which geometry, which configuration the universe was permitted to begin in. Not a mechanism operating inside the universe. Those all require the universe to already be there, running, with time available for the mechanism to operate in. This would be a restriction on universes, a rule about which ones are allowed at all. That's what Penrose was reaching for. It's what Hartle and Hawking were reaching for when they specified which geometries count in the sum. It's what every one of these approaches has been circling. A second category of law, standing alongside the laws of evolution rather than derived from them, doing a job the equations of motion were never built to do. And since we're near the end, I'll tell you which one I actually find most convincing. Not because my preference should carry weight. It shouldn't, and I want to be explicit that this is preference and not fact. But you've stayed this long, and you're owed an honest answer rather than a tidy neutrality. I think the law of initial conditions framing is the most honest one available. Not because it explains the most, it explains the least. But it's the only one that stops pretending the problem has been solved. Inflation, at its most confident, can sound like a closed case. The no-boundary proposal can be presented as though the question of the beginning is finished. This framing doesn't do that. It says, here is the shape of what's missing. Here is what kind of thing would have to exist to fill it, and we do not have it. Naming the gap accurately is worth more to me than a solution that quietly relocates it. And now the counterweight, immediately, because I'd be doing you a disservice otherwise. There's a serious objection to that preference, and it's this. A law that exists purely to specify a starting state is uncomfortably close to describing the mystery rather than explaining it. What does such a law do? It doesn't govern anything. It doesn't predict a process. It has one job: to declare that the universe began this way rather than some other way. And you could reasonably say that's just the original observation, dressed in the vocabulary of law to make it sound explained. We noticed the universe began ordered. We've now written the universe was required to begin ordered, and called it physics. Plenty of physicists find that deeply unsatisfying, for exactly that reason. They'd rather keep pushing on mechanisms, keep looking for a dynamical account, on the grounds that it's a law has historically been what people say right before someone finds the deeper reason. They might be right. I don't know. Neither does anyone. So let me finish with the thing that's actually been underneath all of this, which I don't think is a paradox at all once you see it properly. I think it's the most important fact about your existence. Of all the beginnings, physics appears to allow every configuration the universe could have opened in, every arrangement of matter and energy and geometry, the equations would have accepted without objection. The overwhelming majority are messy, chaotic, violently uneven, collapsing into black holes almost immediately, everywhere at once, space-time knotting up on itself before anything can form. No galaxies, no stars, no chemistry, no structures lasting long enough to be called structures. Dead, in the fullest sense of the word. Not dead as in life ended, but dead as in nothing was ever going to happen there. And then there's a vanishingly narrow class, smooth enough to expand instead of collapse, uneven enough, but only just, only one part in 100,000. For gravity to find something to grip and slowly grow into galaxies. Low entropy enough, gravitationally, that there was an inheritance to spend, and so an arrow of time, and so a direction in which things could happen at all. That last one is the piece people miss, and it's the deepest. The order at the beginning isn't just why there are stars, it's why there is a past. Without a low entropy beginning, there's no thermodynamic gradient, and without a gradient there's no direction, and without a direction there's no difference between before and after. No causation, because causes precede effects, and precede needs a direction. No memory, because a memory is a record, and records only exist in a universe where the past is fixed and the future isn't. No sequence, no history, no possibility of anything accumulating into anything else. Every process you've ever witnessed, every thought you've ever completed, every sentence of this film unfolding in order, all of it runs on that inheritance. You are able to remember the beginning of this conversation because the universe started tidy. Ours came from that narrow class. The universe was dealt the perfect deck, once, in a single deal. And everything that has ever existed is downstream of that hand. So the order in the early universe is not a footnote to cosmology. It's not a technical curiosity for specialists. It is the reason there is a past, and a future, and memory, and causation, and anyone here to notice any of it. Which is why I don't think the greatest paradox of the Big Bang is that the universe began. It's that out of almost every beginning, physics appears to allow, nearly all of them chaotic, nearly all of them dead, ours began in the one condition that could produce a past, a future, and observers capable of asking why. So I'll leave the question with you, properly, because I don't have the answer, and neither does anyone else. Of the five, inflation, Weyl's rule, the rounded edge, the timeless equation, or a separate law of initial conditions, which one do you think is actually pointing at the answer? And which one is just moving the mess into a smaller closet?